Okay, today we tackled turbulent pipe flow, and specifically head losses in turbulent pipe flow. Head loss in turbulent pipe flow is going to be given by the head loss is given by the Darcy-Weisbach equation, which we talked about both today and at our last lecture, F L over D V squared over 2G, plus the sum of any minor losses, V squared over 2G. A little bit cut off there, but you get the idea. So the minor losses are those due to bends, valves, expansions, contractions, and so on. And then the major losses, or the frictional losses, is due to the friction along the pipe walls. And F now is the friction factor. Dimensionally, just on dimensional grounds, we expect F to be a function of the pipe Reynolds number, which we introduced last time, and a roughness ratio, which I'll use Ks over D. This is Reynolds RE. The Reynolds number is V times the pipe diameter. Let's see if I can undo that. Nope. So I'm going to just rewrite that, I think. The Reynolds number is V times the diameter divided by the viscosity, and the roughness length is just a length scale. So the method by which we can estimate this function or calculate this function is using the Moody diagram, which is what's given here on this screen. And so I want to just take a minute or so to talk about how we navigate the Moody diagram. So on the right-hand side, we have the pipe roughness, Ks over D, or in this one, it's epsilon over D. And on the x-axis, we have the Reynolds number. So the Reynolds number being the pipe Reynolds number, Vd divided by kinematic viscosity, or as they've written it here, absolute viscosity and density get involved. The left-hand side is the friction factor that we're seeking. And so if we think of the friction factor F, noted in green, is on the left. So how do we go about reading this diagram? We start, let's say that we know our pipe roughness. So we start at some value of that, let's say 0.01, and we follow that curve into the Moody diagram until we reach the Reynolds number, let's say it's 10 to the third, that we're interested in. At that intersection, we then read across to the left to get our friction factor. In this case, it'd be 0.022 or 0.023. If in the problem you're solving for a flow rate, then we need to iterate. And in an iterative solution, we first guess a Reynolds number, then solve for F, then use energy to get V, and then that feeds back to a Reynolds number. What usually happens in that case is, let's say that now our roughness is some other value. Let's say it's 10 to the minus 4. Let's take a guess of our initial Reynolds number being very, very large. That gives us a friction factor of 0.013 or something. And let's say we calculate and get a smaller Reynolds number that forces us to step down. And you know what? We get the same friction factor again, but maybe it shifts up a little bit. We step down. At some point, it's converged, and that becomes the solution. Usually 2 steps, 3 steps is sufficient. Last thing I'll point out on the Moody diagram is this regime on the left-hand side, the laminar flow regime. This is at a Reynolds number of 2,000. Below 2,000, the curve is linear on this log-log scale, and it represents 64 over the Reynolds number, which in our last lecture we talked about that being the exact friction coefficient for laminar flow. All right, kind of a messy slide here, but hopefully this allows you to see a little bit about how to use the Moody diagram.